Another of the applications of generating functions is to calculate the expressions like this, which turn out to be very complicated, in a well, transform them into a way that is more manageable, right? Okay, let's try to do this. Normally, what you have to do is, well, you have here this expression, right? And after you do the sum, right? So you just run over the index j. J doesn't appear because j is it's just an index that is running from k to n, right? The result, of course, is a function that depends on n and on k, right? It depends on these two variables, right? But what you have to do is to figure out which variable you have to deal with. Well, it pretty much depends on the problem, but let's try in this case with n, right? And if it with n doesn't work, then you can try with k. So let's try with n, and k is going to be a parameter. So for us, this expression is going to be something, a sequence, right, which depends on k as a parameter, right, but n is the index of the sequence, and n goes from 0 to infinity, okay? So from now on, I'm going just to ignore this dependence on k. It's implicit there, and it will appear, right, but we're going to consider just this sum. So what we're going to do is to introduce the generating function, okay, for this expression, right, for this an, which is all this, right, and try to calculate this generating function. And once we have the generating function, we will try to expand this generating function, find the coefficients, and then the coefficients will be equal to this expression here. All right, so let's do that. And then we have the generating function is going to be the sum from 0 to infinity, and then you have set to the n, and then an. An is equal to this expression, so we just plug it in, this expression, right? So we have this, and then we have n over j, and j over k, xj. Okay, the typical thing we have to do with this is we need to exchange these two summations, right? And then sum over n, then try to fit to see if this is simpler, and then at the end sum over j, right? And try to calculate this in a better way. The problem with that is, you see, n is an index that appears in the summation of j, right? So we can't just swap these two summations, because if we put this in front of this one, then this one depends on an index that is sum in the interior sum, and that's impossible. I mean, this is something that we can do. There is a way to deal with this type of things, but it's more complicated than the trick we are going to apply here. What we are going to do is to exploit the fact that if you have combinatorial coefficients in which this number here is larger than this one, or is negative, then the coefficient is 0. So we're going to exploit this fact, right? Okay, how? Well, first, you see this sum here, right? It goes up to n. If j goes beyond n, then this number here is larger than this number, and this coefficient is 0. So that means that if we extend this sum up to infinity, we are adding nothing, right? So we can freely extend it to infinity, and by the way, we have already solved the problem that we started off from. I mean, the problem of having here an index that is the index of summation of this one here. But we can do better than that. We can just do the same thing with this. I mean, we can change j to be, let's see, yeah, j is smaller than k. If we make j smaller than k, up to minus infinity, what you have here is, if it is positive but smaller than k, this number here, this combinatorial coefficient is going to be 0, right? Because you have this number smaller than this one here. So this is 0. And if it is negative, is this one the one that is going to be 0? So you just add nothing if you do that, right? So we can easily extend this to minus infinity. The nice thing of having this, as I explained in theory, is that if you have the sum of from j minus infinity to infinity of xj, that is equal to the sum from j minus infinity to infinity of xj plus p for an arbitrary p. The reason is, by doing this, we are adding over all the indices, all the integer indices here. But by doing this, we are doing exactly the same. It doesn't matter if we are shifted this. But sometimes this shifting is handy, right? And it's useful to simplify the expressions. So we can just do that if we have the summation like this here. Okay, now we can exchange this to limits. There's no problem in that, right? Let me write this like this. So we are summing over all integers j, right? Now we have to introduce the sum over n, but if you look at this, these two terms depend on j, but they do not depend on n, so we can bring them out of the second summation. So we can bring them here. And then add the sum from n0 to infinity of z to the n, and then n to j. All right? N over j. Okay, now let's focus on this sum here, right? You have the sum from n0 to infinity, z n over j. Right, we're adding from 0 to infinity. That means that if n is smaller than j, this coefficient is going to be 0. So this sum is identical to the sum from j to infinity. Okay? Like this. This is equal to that. Right? Okay. If we have an index n that begins at n, then we can change it by an index m, like this, which begins at 0. So we can replace the sum here from the sum from m equal to 0 to infinity, right? Because when m is 0, n is j, and it goes all the way up to infinity. And then every time that you see n here, you can replace it by m plus j, right? And the same here, m plus j and j here. And of course, this set to the j here, right? Well, this can be factored as set to the m, set to j, right? And set j does not depend on m, so if it factors out from the sum like this, we have the sum from 0 to infinity, set to m, and here we have m plus j over j or over m. Doesn't matter. I mean, it's the same. This is the same combinatorial number because the sum of these two is equal to this one here. This is the duality of the duality property of these combinatorial numbers. But this is a sum that we now recognize. This is the sum of 1 over 1 minus z to the power j plus 1. So we have transformed this, and there's no longer a sum, right? So we have z to j over 1 minus z to j plus 1. Okay, then I can replace this sum here by this expression, right, and continue. So we have f, right, which was equal to this sum here. This is the sum from j over all the integers, right, and then you have the sum of this combinatorial number, then you have xj, then you have zj, and then you have 1 minus z j plus 1. Plus 1. All right? Okay. Now we have a much simpler expression here, right? To begin with, the denominator has this form. It's 1 minus z to j times 1 minus z. It's better to leave j here because it's the same exponent as we have here, so we can put everything just as a single fraction. So let's take out one factor, 1 over 1 minus z, and then we have here the sum on j, right, of j over k, and then here what we have is xz divided by 1 minus z to the power j. All right, but again, as we had before, we're adding over all possible integers, but whenever the integer j is smaller than k, this coefficient is going to be 0, so we can as well start at k, right? Because all that there is below k contributes nothing here, right? And this goes all the way up to infinity here. Okay? And as we did before, we can just replace j begins at k, so we can just replace j by k plus, I don't know, t, let's say. So we have 1 over 1 minus z. Let me just write it down here because there's more space, right? So we have here 1 over 1 minus z, right? Then we have the sum from t0 to infinity, because t equal to 0 corresponds to j equal to k, right? And all the way up, okay? Then we have here, instead of j, we write this, k plus t, right? We can write here k or t, doesn't matter, because of the duality of the combinatorial numbers. And then we have here x z over 1 minus z k plus t. All right, there are two factors here. The first factor to the k and factor to t, right? Factor to k doesn't depend on t, so we can take it out. So what we have here is x z to k, right, up here, divided by 1 minus z to k plus 1, right? So this k here plus 1, because we have another factor there. And then we have the sum from t equal to 0 to infinity of k plus t over t, and then this fraction 1 minus z to the power t. Again, this is something that we recognize. This is just 1 over 1 minus this x z 1 minus z to the power k plus 1. K plus 1, right? Okay, let's put it here, right? So we have x z to the power k, and we have here 1 minus z to the power k plus 1, right? And we also have here 1 minus x z, sorry, this is in the denominator, so it's 1 over 1 minus x z over 1 minus z to the power k plus 1. All right, but well, we can simplify this a little bit. To begin with, you see, there is this factor to the power k plus 1, this other factor to the power k plus 1. We can put them together. So what we have is, in the numerator we have this, okay, and in the denominator we have, if you multiply these two factors together, what we have is 1 minus z here, and this factor multiplied by 1 minus z cancels the 1 minus z, and we have x times z to the power k plus 1 there, right? Okay, can we write this in a different way? Well, slightly. We can put x to the k here, z to the k here, and this one here can be rearranged a little bit, just like this. It's 1 minus 1 plus x times z to the power x plus 1. K plus 1, sorry, k plus 1. Okay, this is the generating function, right? Of course, it depends on k, as announced at the beginning, right? Depends on k. But now it has a very nice form to expand it, because we know the expansion of this. Okay, if we have this function, we can easily expand it like this. We know this expansion. This is the sum from n0 to infinity, right, of m plus k over n, and here you have w to k, right? Instead of w, what you have is this. Okay, so this function here is equal to x to k, z to k, and then you have the sum from n0 to infinity, and here we have n plus k, and here you have n, right? And this is 1 plus x to the power, sorry, I brought here k and it's n, I'm sorry, to the n, and here you have z to the n. That's right. Okay, right. We don't care about this, but we do care about this because this is a variable z, which describes the generating function. So we have to group this factor with this other one. So let's do that. So what we have is this. We have x to k here, right? And then we have the sum from m0 to infinity, okay? And then we have n plus k, n, then 1 plus x to n, and then we have set m plus k here, right? And we can change the variable, right? We can say that m plus k is equal to m, okay? Which means that for n equal to 0, m starts at k, and then we have x to k, the sum from m equal to k to infinity, and then we have this is m, and this n is m minus k, okay? And then here we have 1 plus x to n, which is m minus k, and finally set to m. Now we can identify the coefficient here. The coefficient, right? The coefficient of this term, the one that we will call in an k. Well, the letter I'm using here is m, but this is just because it came up this way, and I can just call it n as well, right? This coefficient has this form, is n over n minus k. And here you have x to k, and here you have 1 plus x n minus k. This is the final form. And as you can see, there are no coefficients for powers smaller than k, but that makes sense because if if this index x is smaller than k, then this number here is negative, and then you know that the binomial coefficient is 0. So this is the final sum. So the sum that we have at the beginning of the problem, this one here, right, this complicated sum, turns out to be just equal to this expression here, which is much easier to evaluate, right? Of course, you can use the duality of the binomial coefficients to write this in a better way, like this. N over k, okay? Which is probably much cleaner or much nicer to write down, okay?